Oh, hi there. Didn't have enough review from video 1? Me neither. Let's keep trucking. A few things. You need to know the base definition of some of these terms. So current is the amount of charge per unit time that passes by a certain point. So I equals Q divided by T. Current is measured in amperes, which interestingly enough is a coulomb per second. Resistance, measured in ohms, slows the flow of current. And voltage is the amount of energy per unit charge of a certain region, joules per coulomb. The biggest and baddest part of this circuit analysis is Ohm's law. V equals IR. Voltage equals current times resistance. It can be applied to an overall circuit, so the total voltage of a battery will equal the total current that it's spewing out at any given time times the total resistance of the circuit. Or it can be applied to a single resistor, so at resistors, the voltage that was gained in the battery, it gets dropped off at a resistor. And that drop equals the current through the resistor times the resistance of that resistor. Or it can be applied to a simplified group. So if I've got a chunk of parallel resistors, I could break them down and find the resistance as if there was only one resistor there, and do V equals IR on that, what I call ghost resistors, to figure out the voltage drop, for example. Speaking of voltage drop, you need to know the voltage rule. Now, through the course of one single path around the circuit, the voltage gained from the battery equals the voltage dropped. Notice, for circuits that have parallel components to it, one path around the circuit does not hit every resistor. So do not assume for a given circuit that the total voltage dropped over each resistor equals the total voltage of the battery. Not necessarily true. You actually need to chart a path from the beginning of the battery to the end of the battery and understand that the total voltage gained is the total voltage dropped. And if you have multiple path options, each path drops the same voltage before coming back together. Nice. You also need to know the junction rule. At any junction, at any point in the circuit where you have two paths you can possibly take, the total current going into that path equals the total current coming out of that path. Always, always, always. And that's very helpful for circuit analysis. When you do these circuit analyses, I think that's right, yeah. Don't be afraid of writing all over that circuit picture with current values, with voltage drop values. It should look really messy by the time you're done with it. You'll also need to know equivalent resistance rules. For a series circuit, the equivalent resistance is just the sum of the individual resistances. For parallel, it uses that weird reciprocal rule. So 1 over the equivalent resistance will equal 1 over R1 plus 1 over R2 plus 1 over R3 plus whatever is in parallel. Now keep in mind, this only works for resistors that are in perfect series or perfect parallel. By perfect series, I mean once you go through one resistor, no matter what, you're going through the next one. There is no junction in between those resistors that are in series together. If there is a junction, it ain't perfect series. By perfect parallel, I mean you get to a junction, it splits off, and in each path, there is only one resistor that you encounter before each of those paths come back together. That's perfect parallel. Whenever you've got series, you know the equivalent resistance. When you got parallel, you know the equivalent resistance. For series circuits, the current is the same through each resistor in perfect series, which makes sense. If it's in perfect series, there's no junction, which means there is no place for the current to break off. All the current that goes through the first resistor is going to go through the next one. Versus parallel, the current is not necessarily the same for these resistors. In fact, at each branch, the current has broken off when it arrived at the junction before the branches. So, the sum of the current of each branch will equal the total current that came into that section. For voltage, it's actually the opposite. Voltage is, again, dropped over resistors. So, when they're in parallel, they must drop the same amount of voltage before coming back together. Otherwise, Kirchhoff's voltage rule won't work. When they're in series, their voltage drops add to the total voltage gained. Think of it again as those waterfalls, right? If you've got a series of waterfalls, then their total height will add up to, well, to the total height dropped. Versus parallel waterfalls, the current will branch off, some will go down the left one, some will go down the right one, but they'll fall the same total height before the stream comes back together again. We talked a bit about power of a circuit. Power is just current times voltage. Now don't forget, you can always throw Ohm's law into this as well, and say power is current times, well, voltage is current times resistance. So I could also write power as I squared R if I wanted to, if I didn't have the voltage. Or, I could replace I with V over R, so then the power would be V squared over R. However way you want to slice it, it all comes back to current times voltage. Similarly, this equation works for the overall circuit as well as its individual components. Power is going to be measured in watts, current in amperes, and voltage in volts. We used electrical devices, we just used a digital multimeter. A multimeter can be set up as a voltmeter, which measures voltage, or as an ammeter, which measures current. If you're going to have it as an ammeter, you got to place it in series. These are not magical devices. They can only tell you what they experience. So you have to set them up so they experience the same thing as the resistor you want to measure. Resistors in series experience the same current. So if I want to measure the current, I better put that ammeter in series with my resistor. And it better have very low resistance so that it doesn't change the current. Alternatively, if I want to measure voltage, I better have it set up in parallel with that resistor, because circuit components in parallel experience the same voltage drop. It has incredibly high resistance, because I want to draw as little current as possible through my multimeter, leaving the circuit basically unchanged, as it was before I stuck the multimeter in there. It's actually why you can blow the fuses on ammeters really, really easily. If you accidentally put them in parallel rather than in series, you create a path for the current to go with very low resistance. You could get a short circuit really, really easily and fry out the fuse of the ammeter for safety. Resistivity is the resistance of wires. Well, resistivity is not the resistance of wires. Resistivity is used to find the resistance of wires. So, R equals rho, Greek letter rho, times L over A. Rho is the resistivity. It depends on the material as well as the temperature of that material. R is resistance, rho is resistivity, L is length in meters, and A is cross-sectional area in meters squared. For wires, generally the cross-sectional area is a circle, so I can replace that with pi r squared, where r is the radius of the wire. Like I mentioned earlier, resistivity does depend on temperature too. So rho equals rho naught times 1 plus alpha delta T. Rho naught is some known resistivity for that material, which will be given to you. Alpha is the temperature coefficient, which also depends on the material. It will be given to you. And delta T is the change in temperature from 20 degrees Celsius, whether you're getting hotter or colder. And rho will be the resistivity when you're finished. So if you face a question that involves resistivity, you're first going to want to find your rho value. Once you got that, go back to your resistance equation, plug in your rho value there, and solve for resistance, if that's what the problem asks for. Then we talked a bit about RC circuits. RC circuits are when you put resistors and capacitors together in the same circuit. Now, if you hook it up to a battery, you are going to charge the capacitor. If you unhook it from a battery, you take a charged capacitor and set up a circuit, it acts like a battery that very quickly loses voltage. Now, how quickly depends on the time constant. Time constant, denoted by the Greek letter tau, which you can find here, is simply the resistance times the capacitance, and it's in units of seconds. T, which you can find here and here, T is the amount of time that the capacitor has either been charging or discharging. So the moment you hook it up and it begins charging, the timer starts 0, 1, 2, so on and so forth. Now, epsilon here is the battery voltage or the initial voltage of the capacitor. If it's discharging, it's the initial voltage. If it's charging, it's the voltage the capacitor is trying to achieve. And V sub C is the voltage on the capacitor at any given time. A lot of people mixed up VC and epsilon, so make sure you know which is which before the exam. And next we're going to talk about magnets, but I think I'm going to save that for yet another review video. Tune in